standing as tall as a 60-story building, with blades longer than a football field. Wind turbines are not only masterpieces of mechanical engineering, but also towering giants, reshaping how the entire planet is powered. To bring one of these enormous structures to life, a wind turbine must pass through hundreds of manufacturing stages, from cutting steel and molding composite materials to assembling thousands of components, transporting massive sections, erecting the structure, and finally activating one of the most impressive power-generating machines in the world. Join me to Discovery as we step inside the factory behind one of the most complex machines in modern industry. A single modern offshore wind turbine can generate enough electricity to power around 16,000 households. And across the world today, more than 430,000 wind turbines spin day and night, silently transforming invisible currents of air into electricity that supports the daily lives of hundreds of millions of people. So what exactly is a wind turbine made of? A modern wind turbine consists of 5 main components: 3 blades, the hub, the nacelle, the tower, and the foundation. When the wind blows, the 3 blades begin to rotate, transmitting motion through the hub into the nacelle, the housing mounted at the top of the tower that contains the drivetrain, generator, and control systems. Inside the nacelle, the mechanical energy from the rotating blades is converted into electrical energy. The electricity then travels down through the inside of the tower, passes through a transformer, and is fed into the power grid. From an invisible stream of wind, the entire system works together to generate the electricity that powers everyday life. The manufacturing process of a wind turbine typically begins with the component that directly captures the energy of the wind: its enormous blades. On modern turbines, each blade can extend more than 330 feet, yet it must remain light enough to rotate efficiently while still being strong enough to withstand powerful winds, vibrations, and millions of load cycles over many years of operation. To meet these seemingly contradictory demands, steel is no longer a practical choice for most of the blade structure. Instead, manufacturers rely on high-performance composite materials, primarily fiberglass or carbon fiber combined with epoxy resin. The reinforcing fibers provide exceptional tensile strength, while the resin binds them together into a unified structure, creating a blade that is lightweight, durable, and highly resistant to fatigue. Before shaping begins, the composite layers are brought into the preparation area, where their dimensions, uniformity, and surface quality are carefully inspected. The materials are then cut into sections according to the blade design, ready to be laid into molds and formed into the enormous aerodynamic structure during the next stages of production. To create a blade more than 330 feet long with a shape accurate down to the millimeter, the next step is preparing the enormous mold. Each half of the blade is formed inside a composite or steel mold, nearly as long as the finished product itself, with a surface that is precisely machined and polished to achieve the required aerodynamic accuracy. Before each production cycle, the entire mold is thoroughly cleaned to remove dust and any contaminants that could affect the surface quality of the blade. Workers then apply several layers of specialized release agent across the mold surface. This coating creates an extremely thin barrier between the mold and the composite material, allowing the blade to be removed easily after curing without damaging its surface. Once the mold has been inspected and fully prepared, it is ready for the composite layers to be laid into place and begin forming the blade structure. Once the mold has been cleaned and coated with release agent, the process of building the blade's actual structure begins. Pre-cut layers of fiberglass or carbon fiber are laid into the mold one by one, following a precisely calculated sequence and fiber orientation. In different areas of the blade, both the number of layers and the direction of the fibers can vary, depending on the loads that section must withstand during operation. High-stress areas, especially near the blade root and along the main load-bearing structure, are reinforced with thicker stacks of composite layers. Lightweight core materials such as foam or balsa wood may be placed between the fiber layers to increase structural stiffness without adding excessive weight. Workers continuously align each layer to prevent wrinkles, gaps, or misplacement, because even a small defect can affect the blade's load-bearing performance. Once all the materials have been positioned correctly, the composite layers form a massive multi-layer structure inside the mold, ready for vacuum bagging and resin infusion, which will bond everything together into a single solid structure. Once hundreds of material layers have been positioned correctly, the entire mold is sealed beneath a vacuum film. The pumps immediately begin removing the air inside, compressing all the layers tightly together. Only then is the liquid resin introduced. Under vacuum pressure, the amber-colored resin slowly flows through the fiber layers, filling the remaining voids and bonding everything into a single structure. Once the entire mold has been evenly infused, the heating system maintains stable conditions while the resin cures. After about 24 hours, the hundreds of initially soft material layers have transformed into a lightweight yet rigid composite shell half, ready to become part of the finished blade. Once the two composite shell halves are complete, they move into the assembly stage to become a finished blade. Overhead cranes slowly lift composite beams measuring dozens of meters long and position them inside one half of the shell. These beams form the blade's internal skeleton, carrying much of the load each time the rotor turns. Next, structural adhesive is applied along the bonding edges and at the contact points between the internal beams and the blade shell. Once every component has been aligned, an overhead crane lifts the remaining shell half and slowly lowers it into place from above. At more than 330 feet long, the two shell halves must fit together almost perfectly from the thick root section all the way to the thin, narrow blade tip. During the joining process, technicians continuously check the bonding edges, gaps, and positions of the internal beam structure. Once the two halves are fully closed, they are held firmly in place until the adhesive cures, forming a single integrated composite structure that is lightweight yet rigid enough to withstand millions of load cycles over many years of operation. After the two shell halves are fully bonded, the wind turbine blade enters the finishing and quality inspection stage. First, the entire joint line is ground smooth, excess material is removed, and the surface is refined to match the required aerodynamic profile. The blade is then sanded and coated with a protective layer before inspection begins. Laser scanning systems check the blade's shape and can detect defects that may not be visible to the naked eye. In addition to dimensional and material quality checks, turbine blades must also pass structural load tests. At the University of Massachusetts Wind Technology Testing Center, Haliade X blades undergo millions of bending cycles to simulate more than 25 years of operation. Only after passing these tests are the blades cleared to leave the factory and begin their journey of harvesting energy from the wind. The journey of the tower begins with enormous steel plates measuring around 20 to 50 millimeters thick, with each plate weighing tens of tons. CNC cutting machines quickly cut them to the exact dimensions required for each tower section, while the lower sections are always made thicker and wider to support the full load of the turbine. The steel edges are prepared using an automatic beveling machine before the plates move into a 3-roll bending machine. Under forces of up to 200 tons, 3 massive steel rollers gradually press and curve each plate through multiple passes. With every pass, the plate bends a little more before being fed back through the rollers again. This process is repeated until the once flat steel plate slowly takes the shape of a huge tapered cylindrical section, without developing folds or unwanted deformation. After rolling, each steel plate has become a massive cylindrical section, but it still needs to be welded shut to form a complete load-bearing structure. On a rotating fixture, the 2 steel edges are pressed tightly together before an automatic arc welding machine travels along the seam. The welding arc reaches temperatures of more than 10,000 degrees Fahrenheit, melting the steel edges and filler material to create a solid continuous joint. On larger tower sections, the seam is welded from both the inside and the outside to increase strength. Most onshore wind turbines use towers divided into about 3 sections to make transportation easier. By contrast, the spiral welding technology developed by Keystone Tower Systems can produce towers that are up to twice as tall and up to 10 times faster than some conventional methods. while significantly reducing logistical constraints. Once welding is complete, each tower section must still pass a series of inspections before it is allowed to leave the factory. Ultrasonic testing equipment scans along every weld to detect cracks or internal voids hidden deep inside, while laser measurement systems check the roundness, length, and flange alignment. Once the structure meets the required standards, the tower section is sent through a shot blasting system, where millions of steel particles continuously strike the surface to clean it and create the roughness needed for the anti-corrosion coating. Robots then apply multiple protective layers to both the inside and outside surfaces, helping the tower withstand rain, ultraviolet radiation, and salt-laden air throughout 30 years of operation. Finally, overhead cranes lift each massive tower section onto transport vehicles, secure it with specialized supports, and prepare it to leave the factory for the journey to the installation site. Once the tower is ready, production moves on to the nacelle, the machinery housing often considered the heart of the wind turbine. The process begins with the hub, the central component that connects the three blades. After being cast from steel, the hub is placed on a large CNC machine to finish its surfaces, drill dozens of bolt holes, and machine the bearing seats. Even a deviation of just a few thousandths of an inch can throw the rotor out of balance while spinning. Next, the main shaft, bearings, gearbox, and braking system are precisely machined on CNC equipment and carefully inspected. At the same time, the factory assembles the generator, power converter, and control systems, preparing the complete set of components for the nacelle assembly stage. Once all the components are ready, nacelle assembly begins. On the main frame, overhead cranes position the main shaft, gearbox if used, and generator one by one. After each step, laser alignment systems verify that everything is precisely aligned, because even a small deviation can cause vibration and reduce the turbine's service life during operation. Next, the yaw system is installed so the nacelle can automatically turn to face the wind, along with the cooling, lubrication, braking, sensor, and electrical systems. Finally, the protective housing is fitted around the nacelle, and the entire assembly undergoes functional testing before being packed and prepared for transport to the installation site. While the turbine's massive components are gradually taking shape inside the factory, an equally large-scale preparation process is already underway at the installation site. Bulldozers, graders, and excavators build access roads, level the ground, and excavate the foundation pit for the entire structure. Inside the pit, workers install reinforcing steel, the anchor bolt ring, and cable conduits, before concrete is pumped continuously to form the massive foundation. Once the concrete reaches its required design strength, laser equipment checks the elevation and position of the anchor bolts, while electrical cables are buried underground in advance. The foundation is now ready to receive the turbine's enormous components during the next stage of erection. As the foundation is being completed, another major challenge begins: transporting components that stretch for dozens of meters, and in some cases, more than 330 feet, to the installation site. For wind turbines, this is not simply cargo transport. It is closer to a carefully planned logistics operation designed around each individual route. Tower sections and nacelles, weighing tens or even hundreds of tons, are loaded onto specialized multi-axle trailers to distribute their weight. The greatest challenge is often the blades, whose enormous length makes bridges, sharp turns, and mountain roads extremely difficult to navigate. Before each journey, transport teams survey turning radii, road gradients, bridge load limits, overhead power lines, and other obstacles along the route. In narrow or steep terrain, a blade can be mounted on a blade lifter, a specialized vehicle capable of raising and rotating the blade to negotiate corners that conventional transporters could not handle. The convoy then moves slowly in stages, accompanied by escort vehicles, until the blades, tower sections, and nacelle are safely delivered to the erection area. Once the massive components have arrived at the site, the erection stage officially begins. Heavy lift cranes raise each tower section onto the concrete foundation, while workers align the flanges and tighten hundreds of high-strength bolts to lock each section firmly in place. After only a few major lifts, a steel tower hundreds of feet tall begins to take shape. Next comes the nacelle, weighing hundreds of thousands of pounds. The entire assembly is slowly lifted to the top of the tower, with taglines keeping it stable against the wind. Once the nacelle is secured, the hub and 3 blades are installed. Each blade, measuring about 351 feet long, is carefully brought into position at the hub, precisely aligned with the pitch bearing, and then bolted in place according to the specified tightening sequence and torque. This is an especially sensitive stage, because even a small misalignment at the blade root can affect the balance of the entire rotor. Once the mechanical assembly is complete, the turbine enters the commissioning stage. The control system checks hundreds of signals from the sensors, brakes, lubrication, cooling, yaw, and pitch systems before the rotor is allowed to turn. Vibration, shaft speed, generator output, and power quality are then closely monitored during the first rotations. Only when every parameter meets the required specifications is the turbine approved and officially connected to the grid, completing the manufacturing journey of this giant energy machine. From steel plates, composite fibers, and thousands of individual components, a massive wind turbine has been built through hundreds of manufacturing stages requiring near-perfect precision. In the end, every one of those steps serves a single purpose: transforming the power of the wind into electricity that supports everyday life. That is what makes the wind turbine one of the most impressive engineering achievements in the modern energy industry. Thank you for joining Mito Discovery. If you enjoy exploring the hidden world behind the largest machines and manufacturing processes on Earth, subscribe to the channel and let us know which process you would like us to uncover in the next video.